Hello again, this is Professor McKinsey. I wanted to follow up on one last topic in section 2.1 of the book that we didn't have a chance to touch on in class, and I felt that talking through, looking through a few examples would be helpful as you were doing the reading. So this is the last bit of material on annual percentage rates and annual percentage yield. So this is in the text starting on page 103, where we're discussing what happens when we have an investment of P dollars, where P stands for principal, at an interest rate of R, or percent, compounded annually. The dollar amount accumulated after T years is given by the interest formula A equals P times 1 plus R to the Tth power. So for example, if we were to invest at a 12% annual percentage rate, our investment would increase in value by 12% each year. So at time 0, we would start with an amount of money equal to our principal. After 1 year, our principal would increase by 12%, which means we would be multiplying our principal by 1.12. And that pattern would continue in subsequent years. Each year we would increase our principal by 12%. So in each year we would multiply by yet another factor of 1.12. So that after a total of T years, the amount of money in our investment would be P multiplied by 1.12 to the Tth power. So that's where that formula comes from. We next discuss a generalization of this where our interest rate is still R, but now interest is being compounded n times per year. So what happens when you compound interest multiple times per year? Instead of paying the full interest rate, the full annual interest rate at the end of the year, we'll pay a portion of it several times during the year. Where n is the number of times it will be paid. It's probably easiest to talk about this in the context of an example. So let's take a look at, again, our 12% interest rate, but now compounding it a various number of times during the year. So for example, let's consider what would happen at a 12% annual percentage rate, R equal to 0.12, if it were compounded semi-annually, if interest were paid 2 times per year. So instead of paying a 12% interest payment at the end of the year, every 6 months we'll pay half as much interest, 6% interest. And so twice a year, making a 6% payment. If time is measured in years, at time t equal to 0, we begin this whole process with the value of the account equal to P, our principal investment. In 6 months' time, so when t equals 1/2 of a year, we'll make our first interest payment of 6%. When t equals 1, we'll make our second interest payment. We'll increase our principal by another 6%. And in general, for each year, we will have made 2 times as many interest payments as there are years. So after 2 years, after T years, the balance of the account would be our principal multiplied by 1.06 to the power 2t. If we were to change the number of compoundings, for example, if we were to look at quarterly interest payments where n equals 4, we're paying interest 4 times a year. If our annual percentage rate is 12%, each of those 4 interest payments could be a 3% interest payment. And then we would find that we would start with a principal value of P. Each quarter of a year, we would make an interest payment of 3% of the current value of the account. So the value of the account would increase by 3% each quarter. And so over the course of 1 full year, we will have made 4 payments, 4 increases of 3% each. or in effect, we would have multiplied the value of the account by 1.03 to the fourth power. If we follow that pattern and do this for t years in a row, the total value of the account after t years would be 1.03 to the power 4t. We would have made 4 times t many interest payments over the course of t years, each interest payment giving us a 3% increase. In general, the pattern that we have is that the value of the account after t years is our principal p multiplied by 1 plus the interest rate r divided by n, the number of compoundings, raised to the power n times t. So r divided by n is the interest rate being paid at each time we do a payment, whether it's quarterly or semi-annually or every month or what have you. So 1 plus r over n is the increasing p by the appropriate amount for each payment. The total number of payments per year is n, so the total number of payments in t years would be n times t, and that's what gives rise to our exponent. And so that's where this second formula on page 103 comes from. The two concepts that they're talking about in the reading in this section are the annual percentage rate, or the nominal interest rate, and that's just the annual rate r that all of this compounding is based off of. And in comparison, we can look at the annual percentage yield, the APY, or the effective interest rate, which would be the percentage change in the value of your account over the course of 1 year. When n equals 1, when you are compounding interest, when you're paying interest only 1 time per year, the annual percentage rate and the annual percentage yield would agree. They'd be equal to each other. The distinction between the two only emerges once we start having values of n bigger than 1, once we start compounding interest more than once a year. So I'm going to look at some examples of how that plays out next. If we think of having, as in our earlier examples, an annual percentage rate of 12%, the value of our account is, as a function of time, will be our principal multiplied by 1 plus r over n to the nt power, where r is 12%. And I'm going to see what happens for various values of n. When n equals 1, so this is compounding annually, the value of the account after 1 year, so with both n and t equal to 1, is just p multiplied by 1.12. The annual percentage yield, the percentage increase over our original value of the account p, would just be 12%. And so here our annual percentage yield and our annual percentage rate agree. When n equals 2, if we were to compound interest semi-annually, after 1 year the value of our account would be p multiplied by 1.06 squared. We're making a 6% interest payment 2 times over the course of that year. Now that turns out to be p multiplied by 1.1236 when you square out 1.06. And so our annual percentage yield ends up being 12.36%. That's the percentage by which our principal would have increased over the course of 1 year. If we do quarterly compounding of interest when n equals 4, the value of the account after 1 year would be p multiplied by 1.03 to the 4th power. We're making 4 interest payments of 3% each, and that works out to p multiplied by 1.1255. Well, I'll truncate there. This works out to an annual percentage yield of around 12.55%. This 1.1255 and so on being the 4th power of 1.03. The more often we compound, the higher the annual percentage yield. If we were to set n equal to 12, if we were to compound 12 times per year or make interest payments once per month, if the annual percentage rate is supposed to be 12%, we might think of making a 1% interest payment each month for 12 months consecutively. If we do that, our principal will be multiplied by 1.01 to the 12th power, which turns out to be 1.1268 and there are a few more decimals beyond that. This is an annual percentage yield, or an effective interest rate of 12.68%. The more often we compound interest, the larger the value of n, the larger the annual percentage yield would be. However, while it's true that the annual percentage yield will increase as we choose larger and larger values for n, it does not increase without bound. For example, when n equals 365, if we were to pay interest every single day, we could pay 1/365th of 12% interest every single day. We would do that 365 days in a row over the course of 1 year, and our annual percentage yield would be around 12.747%. So for example, if we were to compound interest every minute, there are 60 minutes in an hour, 24 hours in a day, 365 days in a year. You multiply those together, there are a bit over 500,000 minutes in a year. And so if we were to divide 12% by this 525,600, that would be the amount of the percentage interest we should pay each minute, and we could make 525,600 such interest payments on our principal over the course of a year. That would give us a total of a 12.75% annual percentage yield. And it turns out that we could go to compounding every second, or every tenth of a second, or every hundredth of a second, and these percentage yields are going to have as a limit a number just a hair bigger than this 12.75%. And so when we talk about continuous compounding of interest, it's thinking about what happens in the limit as we let n get larger and larger and larger, as n goes to infinity, as the number of times that we pay interest per year grows without bound. If we pay interest more and more and more frequently, it turns out that the value of the account after t years approaches in the limit our principal p multiplied by e to the power rt, where r is our annual percentage rate and t is the number of years. And so at the end of 1 year, when t equals 1, if we have a 12% annual percentage rate, as we've been looking at, this e to the 0.12 power is the limit of the annual percentage yields that we were seeing as we took larger and larger values for n. And it turns out that the best annual percentage yield that you can get from continuous compounding of interest is this 12.75% that we're seeing as the percentage growth rate over the course of 1 year. So hopefully this has been a helpful exploration of where these formulas come from for the value of an account with various compoundings of interest, and the distinction that we're drawing between annual percentage rate and annual percentage yield.